Well, you have probably seen the overview talk. There, I have roughly given you a very brief idea about the various important concepts related to the field of stellar structure. Now, after this talk, I felt that, so I was saying that after the talk, I feel that there are certain points which probably I have skipped, giving you the overall picture. So I'll try to cover up those missing points. And again, certain other important concepts which have been entirely skipped overall. Okay. So let's again start from the very beginning. So as I was saying on that day, well, sometimes the very fact that we don't see anything at all, we don't see any changes at all, it is even an indicative of a great deal of information. Okay, so the very fact that we observe neither the brightness nor the color changes in stars for centuries. We had observations, you must know. So what does this mean? So what I am saying is that no change in brightness and no change in color. Now you see, these two very basic informations tell us everything about the stellar structure. Now this is the greatness of physics. You see, just from very basic observations and using very basic principles of physics, you can extract so many things without even going to go over to that place. Say for the sun, how far it is? Very far. And even if we are able to go there, we will just perish. But you see, I will just show you that within 5 to 10 minutes, using just basic ideas, you can get so much information. So let's start. So you see, what does it mean when I say that no color change is observed for the stars? Of course, you do know that the color represents, remember, Wien's displacement law of black body radiation. So if I assume, which has been seen to be approximately good as well, that the entire energy of the star can be approximated by the black body radiation energy distribution, and it has been found to be correct, then I can extract the effective temperature of the star, and from there I can extract the color, right? So no change in color of star. This means T effective remains constant for the star. Now remember the brightness. So what is brightness of the star? So brightness is basically related to your luminosity, right? And what is luminosity? 4 pi radius square into sigma, this same T effective to the power 4. Now as I was saying, since T is constant and also no change in brightness is observed for centuries. So what does this mean? This means L is also constant. Now you see on this equation, this is constant, this is constant. Now 4 pi and the sigma, they are constant. So the inference is radius, we have a constant radius for the most of the stars that we observe in the sky. Now I am saying most of the stars, there is a catch. There are pulsating stars as well. Anyway, let me talk about the main sequence stars. So the entire thing now revolves around this, the fact that effective temperature is constant and the radius of the stars is constant. Now you'll see that these two facts tell us a lot about the interior structure of the star. Okay, now first let me talk about the constant radius. Right. Okay, so you see that, of course, we know that the large interior mass, a star has a very large interior mass, right? Now this large interior mass exhibits a very large inward gravitational force, right, on these external layers and so on and so forth. The force is, what does it try to do? It tries to pull the entire matter inward. Now, the fact that the radius is constant means that there must be an equal and opposite force acting against the gravitational force. And this is basically the pressure force. Okay, and this force is again the same which prevents our Earth's atmosphere from collapsing. And you see the equilibrium, since we have constant radius, so we have equilibrium between this pressure force and the gravitational force. And this equilibrium statement is given by the hydrostatic equilibrium equation. Well, this state is known as the state of hydrostatic equilibrium. This equilibrium, okay, so yeah, this equilibrium state is known as hydrostatic equilibrium, and the equation which basically is the mathematical statement is known as the equation of, you do remember it, right, that we have derived this on previous occasions. So basically it gives us information about pressure as a function of the distance from the center. So dp dr is equal to minus rho r g mass enclosed is inside this r, again distance from the center, divided by r square. Okay, so very important point is this negative sign, which means that dp dr is negative. That means this pressure, it actually increases as r decreases, as we go towards the center. Okay, now this is in fact one of the first equations of stellar structure, first stellar structure equation. Now you see, in general, other forces may also be considered. Say for example, the centrifugal forces for rotational stars, or even electromagnetic forces for magnetic stars. But one thing that is I would like to point out is that this equation is valid only when there is no radial motion. So hydrostatic equilibrium means basically no radial motion. But this is not always true. You see, in the rapid evolutionary phases of the star, such as the supernova phase, or when the star is pulsating, as I was just saying previously, this equation is not valid because we do not have the hydrostatic equilibrium at that time. And therefore, we have to consider the equation of motion, which is the more general equation. Equation of motion. Again, you must remember that I have also derived this. So the equation of motion was, remember, it was of this form: d2r dt2 is equal to minus rho gm by r minus dp dr. And only when there is no acceleration of a pocket of mass, then this term is zero and we have hydrostatic equilibrium. And remember, when we have to use this equation, then the hydrodynamics of the medium has to be considered. Now I am not going to talk about it because right now we are considering the equilibrium state. We are considering our star, our sun as an example, which is a main sequence star, and there is no change in the radius of the sun as well at all. Okay. Now, what are the consequences of this hydrostatic equation? Consequences of this hydrostatic equilibrium. You see, you must remember this. We have derived this. One of the greatest consequences is that we can estimate the gas pressure at center. You remember? We have discussed this apart. Now I am not going to write down all the detailed expressions, but I am just going to point out what we have covered. And you see, if we estimate the gas pressure, and again we use the ideal gas law, or ideal gas equation of state, then we would be able to estimate the central temperature Tc. Now this is the greatness. Suppose I ask you to find the temperature of your nearby sitting friend, what will you do? You will go take a thermometer, come back to him, put the thermometer either in his mouth or in her mouth or around the elbow, and you will wait for 2 or 3 minutes. But you see, here we don't have to take so much time to estimate the central temperature of the sun, which is so far away, or the nearest star for us, and we are just using what? This hydrostatic equilibrium equation and the ideal gas law, and we can just estimate. So remember, this estimation is just using the hydrostatic equilibrium equation only. Now there are other ways of estimating this temperature as well. I will come to that. Now, what the result was that upon doing the estimation, we found that the central temperature, it can reach values of the order of 10 to the power 7 Kelvin. What does this mean? This value itself means that the central temperature, if it is so very high, then nuclear reaction will be possible. So this means just from using this hydrostatic equilibrium equation, and using the ideal gas law, we are able to get an idea about the source of the energy generation in stars, which could be nuclear reaction. Right? Now, you must be wondering, why are you saying that nuclear reaction could be a possible source? Now you see that what we have at the current moment in the sun is, we are seeing sunlight outside. So what is this? This is basically photons emitted from the sun, or basically heat loss from the surface of the sun. That is luminosity, and we are just getting a very, very tiny part of it as sunlight right now outside. So you see, what I want to tell you is that at every second there is a gigantic amount of heat loss from the sun. Where is this energy coming from? Who is contributing to this energy? Now, I am not talking about gravitational contraction here. Why? Because radius is constant. Remember, we are talking about hydrostatic equilibrium. So when the radius is constant, right now gravitational contraction is not working. We are not going to extract energy from it. So who is the source of this energy? And also the very fact that we have the pressure force against the gravitational force, and this is because of who is the actual source for this pressure. Initially, when the star was contracting from the giant molecular cloud, there, of course, the half of the energy lost due to gravitational contraction was radiated away, but the other half went into the increasing the thermal energy. It was captured, right, to increase the thermal energy of the star. But right now I am talking about the constant radius scenario, that is hydrostatic equilibrium. So there must be a source which is the real reason for constant thermal temperatures throughout the star. Say for example the surface, we are seeing a constant temperature throughout the star. So let me talk about the next part first. So as I was saying, we observe not only constant radius but also no change in color. Yeah, remember. So no change in color, this means constant temperature. That is surface temperature T effective is constant. Now, so surface temperature is constant, and this is in spite of losing energy at surface, right? So what does this mean? These two facts, they mean that the star is in so-called thermal equilibrium. And what does this mean? This means that energy radiated away or lost from the surface is happening at the same rate as produced by some source. And as a result, the star maintains constant internal temperature profile, T profile, right? Or that means you can say that at each radius or distance from the center, star is neither heating nor cooling, right? Now let me write down luminosity. So luminosity of a mass pocket which is at a distance r from the center, what will it be? The luminosity from that mass pocket is basically the mass of the pocket into Q. What is Q? Q is basically the rate of energy generation per unit mass. Okay, and so we have, you see, this relation, and this dm I can write 4 pi r square into rho dr. This is basically the dm. So this is the star, and I am just considering a pocket of mass m dm at distance r. So I am basically considering a shell around, and that mass is dm and the shell thickness is dr, and so this is dm. So this means that I can get this relation, you see, dl is equal to 4 pi r square rho dr into q, and this is basically the equation of energy conservation. Okay, so this is yet another equation of stellar structure. Regarding this, I must tell you that this Q is basically equal to dF dm. And what is F? F is basically the radiant heat flux. So you see, first we talked about the equation of hydrostatic equilibrium. Basically we learnt about the pressure profile. Next we are talking about the luminosity. So we are able to get an idea about this luminosity from the equation of energy conservation. Okay, now what about, I have said that the temperature is constant throughout. This doesn't mean that the temperature is the same throughout. What I want to say the temperature Tc at the center and the T effective at the surface, they are the same throughout time. But this doesn't mean that the both of them are the same together. No. This Tc, if it is of the order of around 10 to the power 7 Kelvin, it remains like that. And this T effective is of the order of 5800 Kelvin. It remains like that. This is what I want to say by thermal equilibrium. Now you see, there is a huge temperature difference. So this means that there is a great temperature gradient, and this means that there is an energy flow. Of course there is an energy flow. That's why we are seeing the sunlight, right? So next I would like to talk about this temperature gradient. That means dt dr. How do you talk about it? But before that, let me tell you that around this core, the mean free path of photons is of the order of, I'm not going to estimate, I'm just giving you the result, of the order of 1 centimeter. And in this dimension of 1 centimeter, the change in temperature compared to the central temperature is of the order of 10 to the power minus 4. So this means that effectively, if we consider a region of the order of this mean free path or so, then here, including temperature, other thermodynamic quantities remain essentially constant. And so, even though the temperature is gradually changing by large magnitudes, we can have a small region of space where we can have a local thermodynamic equilibrium. Remember, in stars, we never have a global thermodynamic equilibrium. You see, because of this temperature difference. But we can have a LTE, local thermodynamic equilibrium. And then, if we assume that this energy flux is a result of the diffusion of photons from the core to the surface, then just by assuming this diffusive nature of photons while transportation, we would be able to derive this dTdr and get an estimation of the luminosity. And that is your equation, third equation, which is basically the equation for radiative energy transport. And this is how we are getting this. Okay. Now let me talk about the last equation, which is basically the equation of continuity. Again, same thing, shell, mass, dm, and so we can write dm is equal to 4 pi r square rho into dr, or dm dr we can have. And that is basically the equation of continuity. Now you see, from this equation we can either use m or r. This I have already discussed previously as well. So I have roughly talked about the various cases, various basic stellar structure equations. We have talked about hydrostatic equilibrium. We have talked about the thermal equilibrium, and even the local thermodynamic equilibrium. Good. So again, let me come back to this old question of who is maintaining this hydrostatic equilibrium? So who maintains this? Who maintains hydrostatic equilibrium and constant luminosity? Again, who is the one? And the answer is, the source of the energy is the nuclear fusion. Well, come on, if we have, you see, what you can suppose I have a cup of tea and I know it is losing energy by radiation. So it cools down unless I keep heating it. Now what is happening here in the star is that the very fact that the colors don't change, from there I am inferring that the temperatures don't change with time. So this means that the surface layers must be heated from below. And this means that the same amount of energy must be supplied to the surface layer each second as it is taken out each second by radiation losses. Okay, by radiation. And so this source is basically the nuclear fusion. You must remember this. Hydrostatic equilibrium is due to this nuclear fusion. This is the reason. Now let me tell you something more. So you remember I talked about this Q, rate of where was it? Rate of, here. So Q basically rate of energy generation per unit mass. Now let me tell you that this Q is highly temperature dependent. Okay, so basically this Q, I am not showing you the result, but it can be worked out that this Q is proportional to, for two body reactions, proportional to density and temperature to the power some number. And this number, say for the hydrogen PP chain reaction, the slowest reaction, which will determine the reaction rate, for this nu is of the order of 4. And what about the CNO cycle? Again, another possibility for hydrogen burning. For there it is of the order of 20. So you see, this energy generation rate per mass is highly temperature dependent. Okay. Now, because of this, also we have this self-regulation in stars through a negative feedback. So, self-regulation through negative feedback. Let me show you how. Well, suppose the fusion rate goes up. So as a result, this Q will increase. Or what will happen is that temperature will increase. And as a result, the gas pressure, it will increase. And so what will happen is that it will be dominating over the gravitational force and our core expands. Now when core expands, what will happen is that density will decrease and also temperature will decrease. So you see, now as temperature decreases, this Q, what will happen? Q will decrease. So we have got a negative feedback mechanism, and this is the reason for the self regulation in stars.